Assalamualaikum and hi. Today we like to present our key study, which the title is Deep Learning in Predicting the Reactivity Value of mRNA Vaccines. Our group consists of 4 members, which are Chan Ziyi, Pan Choyen, me, Fatina Cha, and Hassanatul Aliyah. We all are aware that every country has faced a COVID-19 pandemic since 2019, which impacted many industry. This pandemic is still spreading and many people across the country have died because of this disease. To fight this disease, several vaccines were developed. mRNA is a suitable candidate vaccine since it has high potency, safe administration, potential for low-cost manufacturers, and also capacity for rapid development. So, in this case study, we will use deep learning, which is the gated recurrent unit, as the prediction model to predict the reactivity of mRNA molecules for each position of the sequence. The mRNA was designed to recognize and respond to the protein produced by the disease, and the findings of this study will be discussed in the evaluation and validation sections.
For the part design solution based on modeling, the model that we are choosing for this project is we choose deep learning model instead of machine learning, which is we use gated recurrent unit GRE model. GRE model is a model under recurrent neural network RNN, which RNA is a dynamical system with temporal state representation. And we use GRE model compared to LSTM because it has an advance of RNN, which is more uncomplicated version of the long short-term memory LSTM network. And GRE model has the latter replaces the input and forget gets in frontier as an update gate, which is it allows training to become easier as it has fewer parameters than LSTM. GRE model also can only choose to maintain or fully abandon all the earning memories. And since GRE model has a similar achievement to LSTM, but we choose GRE model instead of LSTM, it is because it has a lower requirement on the memory. Moving on to the next part, which is exploratory data analysis, which is ADA. This is the partial rows from the training data, and this is the partial rows from the test data. As you can see, the training and the testing consist of two important fields, such as feature prediction field, and the feature fields included sequence, structure, and predicted loop type. And the sequence here represent the A for adenine, C for cytosine, G for guanine, and C for uracil, H for the sample. And moreover, the predicted fields included reactivity secondary structure of the mRNA, degree mg/10 and degree pH10, which is the probability of degradation rate with or without magnesium at high pH. Degree magnesium 50C and the degree 50C, which is the probability of degradation rate with or without magnesium at high temperature. The data augmentation, this is a practice in producing new trained data symmetrically from the current data to increase the performance of the deep learning model. And the trained data was augmented with the wrapper initially used in generating the data, which is the RNA package. In predicting the RNA structure for each sequence, the Vienna-2 package is used. It is dependent on the thermodynamic experiments and obtaining the structure by laying the position of the lowest possible entropy. There is an alternative method in augmenting the data, which is contrafold. It is an approach that utilizes statistical method in predicting the structure. With data augmentation, the amount of trained data is increased, which helps in enhancing the effectiveness of the training of model. It is due to every sequence can produce the structure and predicted the types. For the occurrence number of the new generated data and the original data, it can be referred to this figure.
This show the GRU model architecture process. We will have the input data, and since the input data cannot be used already by the GRU model, we need to do feature extraction. So after we generate some useful information for the GRU model by feature extraction, the GRU model will use the information to produce the output, which is the reactivity value of each sequence for each single base. This is the output that generated by the GRU model, which each sequence will have each base, and then the reactivity value is displayed. For evaluation and validation of the model, we will use the mCRMSE mean column-wise root mean square error to assess the performance of GRU model. The smaller the mCRMSE value, the better the performance of our GRU model. For our mCRMSE value obtained in this project is 0.239, and when we refer to another paper that doing the similar studies, the mCRMSE value obtained is 0.128. There is a difference of 0.111. So when we observe the graph that generates from our project, which is on the left side, the trained data and validation data also have a big difference in mCRMSE. And then for the right side is the mCRMSE value of the loss and the trained data and validation data also, but the difference of them is smaller. So it can be concluded that our GRU model performance is not that good as the hybrid model in the reference paper because we use a different model. The reference paper combined of LSTM model and also GRU model, but then we only use the GRU model. This is one of the reasons that we obtain lower performance than the reference paper. So that's all from us. Thank you.